showing you the same if you have a ground bed with impressed currents and you have a line that runs in that magnetic area. Current will be picked up around the anode and will be discharged in other locations around it. You have it with trains. If you have a positive, the orientation is, the polarity is extremely important, as you probably can imagine. If this was a magnet, the currents would go the other way around. So if you have a current feed and the return current in the rails to the transformer station, some of the currents, if they have a lower resistance path here to soil, they can run in other metallic structures, and they would cause corrosion here where they go back to the transformer station. Same thing with overlying trains. You can have stray currents and risk of corrosion at the foundation levels. Polarity again is highly important. This is the Bucharest Metro. Very often in tunnel segments, these are not in continuity, one segment to the neighbor one. That's by choice. They had selected to make them in continuity, which can also be a good idea. But you then have a very long path that the current can run, so you can actually add your effects up that way and make it even worse. They had not been quite consistent. These bonds were missing in a number of places. We did measurements on the conductivity following one of the European codes on this, where we can measure if there's a certain leak to the tunnel structures next to these rails.
Sorry, what are those links? I didn't understand.
Which ones? These?
No, the links that you show between the segments.
These?
Yes.
They're continuity straps, so that you have continuity between all of the, and that you can choose whether you have that. Sorry?
Electrical continuity.
Electrical
Forcing
continuity.
steel, so if there's a stray current, it goes around and goes over a larger area.
Yeah, that would exactly. That would mean that the stray currents could run in a longer distance. If you had them isolated, it would also limit the problem to some extent. Many of our new design, they're not with straps here.
So the current that goes in is gonna go.
So the current, if there's a stray current from this system that goes out somewhere in the rail, being picked up in the tunnel,
Yes.
goes out somewhere,
Yes.
it would then be the amount of current in the area in here. And you could have the same system here. It could also jump from one to the other. If it does that, you would have a pick-up and discharge and pick-up and discharge location. These things are very complicated. But by principle, the different strategies can be used for doing this. Basically, what you aim at is that you have a very low conductivity in this area, so you will not have stray currents running out of your rails, causing corrosion. But for practical reasons, that could be very, very, very difficult to obtain. We know that from some of the measurements that we've done, also on the Copenhagen Metro. You can see here, I mean, built off of debris. Very, very difficult to have a high maintenance tunnel structure. This is of course a bad example, but when you have trains operating here, iron dust will come. And if you go to some metro station, you can do this and you're completely blank. So you have a big coating around your tunnel, which is a very good conductor. So that so even with the best of ambitions design-wise, you can still have a problem. Furthermore, in the design codes, conductivity design values are very low. We're talking about millisiemens per kilometer. Siemens, that's reversible of ohms, so that's to do with resistivity. This only takes your structure into account. It only looks at how this design is made with these rails. It does not look at any foreign structures that could affect your structure. And that is very important to know. Especially with all the city traffic that we have. There are different city traffic. There could be trams. If you talk about San Francisco, you have tram system, they are direct current operated. So they could actually make stray currents by themselves causing interference on other structures. So if you bring on a new structure, you really, really need to map where things are. So imperfect insulation is a big issue. Build up of debris. We did measurements of least conductivity. We had a local guy with us. We took the battery out of his car to do these measurements. So this is a 12-volt car battery. And what we measured was between 60 and 425 Siemens per kilometer. This is millisiemens, this is Siemens. Also, we did measurements where we had reference electrode we mounted on the tunnel elements, and at 3 different locations during operation of the tunnel, and we could then follow the peaks from trains driving past this location. This is another example. That was as much as I had just now on metros and stray currents. Just on that one, I have another example in a minute. This is a bridge in the south-western part of Denmark where we did a cathodic protection installation. So the piers are having cathodic protection, and below water we have also ingress current cathodic protection. These are DC operated. We have on the pier column below water we have a wiring system where we have monitoring on how this system performs. The diver himself said that when we did 1 year inspection of this, I forgot to connect it to the negative terminal. This was what it should have been like. This is what it looked like after 1 year. Completely gone. The diver says, I forgot it. This is on me. So he went down there and made a new connection. Stray currents, of course, it's placed directly in an electrical field. Very rapid corrosion if you are under. We're now having extension of our metro in Copenhagen. And as I said, we can follow all the codes and standards, but if you have other systems that can operate around you, that may not be sufficient for you to evaluate whether you would have a stray current situation or not. What we've done is that we've evaluated the entire alignment with what are the conditions around this tunnel structure. Which, for instance, are they placed in limestone, glacier, which has a much lower resistance than limestone has, and therefore there could be a higher tendency for stray currents to take place. In some places we have both limestone and glacial deposits on top. Some of it is placed near the Copenhagen harbour area, some of them where we have more water saturated, and all of it in anaerobic conditions, many of them placed in deep below ground, 15 meters or so. We have overlying DC systems. S-trains are the trains that operate on grade level. We know, because we measured it, that they have a very high thing with stray currents. They know that themselves. They have had a building in a part of one of the stations that blew up. A fire took place because they had this arch of. They had some stations they gave up on making surveillance on one of the city stations because of stray currents short-circuiting that camera all the time. So they do have problems. And they operate at another level voltage measuring. In voltage. It's a floating electrical system, so they are not ground to the same system. Therefore it has another potential than the future metro will have.
What are the legal implications of your system creating problems in other people's structures?
That's a very good question. I know that the existing metro, they already had somebody come and say, you are causing problems to us.
Right.
Documentation, first of all, and then the legal system will take over from there, I'm sure. We have these trains, these are places where we have trains crossing the line at different places. It would also be crossing the existing metro And maybe some of you heard that we have an amusement park which is called Tivoli in the center of Copenhagen. All the amusements are direct current operated.